In this video, we will discuss the use of ICE tables to determine our equilibrium concentrations. In previous videos, we talked about the concept of equilibrium being the point at which the rate of the forward reaction and the reverse reaction are equal, and that we have two terms, the reaction quotient and the equilibrium constant, both of which are equal to the concentrations of the products raised to their respective coefficients, those coefficients we get from the balanced chemical equation, divided by the concentration of the reactants raised to their respective coefficients. The difference between the reaction quotient Q and the equilibrium constant K is that the value for K is when the system is at equilibrium, the concentrations of the products over the reactants at equilibrium. Q is that exact same ratio at all other times. So in order to determine the concentrations that we will have at equilibrium, we need to decide first which direction the reaction is going to proceed. We will do that by comparing our Q value to our K value. This will tell us whether the reaction needs to shift to the reactants or to the products. In step 2, we will define the change of all material in terms of X. In some instances, looking at other sources, you might see the delta be used instead of X. It works the same way regardless of whether you use X or delta. We will be using X. This X value is called the extent of reaction. It is meant to indicate how far the reaction proceeds. We will use the coefficient from the chemical reactions as the coefficients indicating how far each one of our components change by multiplying that coefficient by X. The X value will receive a plus for the side of the material where the reaction is proceeding towards, and the minus will be put in front of our X and the coefficient for material on the side of the reaction that the reaction is proceeding away from. By this, I mean if the reaction needs to move towards the products because the Q value is too small compared to the K, so we would need to increase the numerator. Then the products are being formed, and so they would get a plus in front of their respective X values. The reactants would get a negative. However, if Q is less than K, then that means that the reaction has to shift back towards the reactants. And so the plus would go with the reactants, the minus would go with the products. We then solve for X. Ideally, you get some sort of a second order equation in which we can take advantage of using square roots to both sides or some other mathematical tricks. At times, we might need to resort to using the quadratic formula. In most other situations, particularly if you have a third or fourth order polynomial, you will need to either use an approximation method in which we assume that the change in X is insignificant compared to the values that we already have, thus simplifying the equation. We will look at examples using both the quadratic formula and this approximation method. So that's one method, or you would have to solve it using computational methods with computers. In order to determine the concentrations at equilibrium, the process involves multiple different steps and a lot of different moving parts. It is therefore necessary to approach the problem systematically. We will be using what is often referred to as an ICE table, standing for Initial Change Equilibrium. It's a way of approaching these equilibrium processes. Some books, like the Tro textbook, uses SCE for Start Change Equilibrium. Whether you're calling it the initial value or the start value, it doesn't matter in how you actually do the process. So I will be referring to them as ICE tables, where I is initial, C is change, E is equilibrium. We will start by making a table to keep track of all the different things that are going on. The first row, we will write out our initial concentrations. The second row, we write out how each one of our components change, whether they go up in the case of processes where the reaction is moving towards that side, in this case products. We will put a minus in front of the ones that are decreasing in value, in this case the reactants. In our equilibrium row, we will combine the initial and change to come up with expressions for each one of our components. We can then take the values for our equilibrium concentrations and plug them into our equilibrium constant equation, which is the concentration of the products raised to their respective coefficients divided by the concentration of the reactants raised to their respective coefficients. Note that for each one of these, we have small equations for each one of our concentrations that are coming from our equilibrium line. We will now demonstrate how we can determine the equilibrium concentrations using the ice tables for a process involving the Haber-Bosch cycle, or Haber-Bosch process. This Haber-Bosch process is perhaps one of the most important chemical reactions that is done industrially on the planet. It accounts for approximately 2% of all global energy is used for this one reaction. The reason why it is so important is this is our method of synthetically producing ammonia, and ammonia is used as a fertilizer. Without this process, the world population would be going hungry, even if we had converted 100% of the land into crops. So because we have the Haber-Bosch process, our farmlands are much more prolific, enabling us to potentially feed the world population. So the way that we're going to approach this is first filling out our ice table. I find it convenient to first write out your balanced chemical equation, which we have here, giving yourself plenty of space to use this equation to help us fill out our ice table. So directly below the written out balanced chemical equation, I will write I for initial, C for change, E for equilibrium, and then I will fill out the table. So the problem says that at 673 Kelvin, the equilibrium constant for the Haber-Bosch process is about 5.6 times 10 to the negative fourth. If we have a reaction vessel with about half a mole per liter of nitrogen and 1 mole per liter of hydrogen with none of our products, what will the equilibrium concentrations of each one of our components be, and what is the extent of the reaction needed to reach equilibrium? Okay, so we write out our initial concentrations. So our starting concentration for nitrogen is 0.50 molar. Our concentration for hydrogen is 1.0 molar. And our concentration for our ammonia is 0. So our K value, or our Q value, we'll just write out K. Our equilibrium constant is the concentration of our products, so this would be NH3, raised to their respective coefficients. We have a 2 here, so that would be a 2, divided by the concentration of our reactants raised to their respective coefficients. So this would be N2 raised to the first power, because there is a 1 here, times the concentration of H2 raised to the third power. And the reason it's a 3 is because we have a 3 coefficient here. Okay, if we just eyeball the values of putting them into our equation to see what the Q value would be, we note that in the numerator we're putting in a 0. So right now Q is equal to 0. We have 0 over some number. It would end up being 0.5. So 0 over 0.5 is equal to 0. 0 is less than our K value, which means we don't have enough in the numerator and we have too much in the denominator. So the reaction has to shift towards the product. So our reaction will shift to the right. What this means is that we will lose, or our concentration of our N2 will be going down. So this will go down by some value X. Our H2 will go down by, this time, 3x. The reason why it's 3 is because every time the reaction proceeds, we have 3 hydrogens that go for every time the reaction goes to the right. Each time the reaction goes to the right, we will be producing, so plus 2 of our NH3s, and this will go up by 2x. So at equilibrium, our concentration of N2 will be our initial 0.50 minus x. Our value for hydrogen will be 1.0 minus 3x. And our value for ammonia would be 0 plus 2x, or just 2x. Right? 0 plus anything is the same value. So we can plug these into our K value, and we'll see that we get 2x, that whole quantity squared, divided by our value for N2, which would be 0.50 minus x raised to the first power, and then 1.0 minus 3x raised to the third power. Now, if we look at what's going to happen here, we're going to end up with a fourth order polynomial. That is something that we will not be able to solve. So we're going to use our assumption rule. So we're going to assume that our x value is insignificant compared to our other values. Now, judging from our k value is fairly small. It's times 10 to the negative fourth. This is about on the cusp of where it's okay to use the assumption rule. The assumption rule essentially says that our x values are insignificant compared to the values that they're next to. Because our equilibrium constant is so small, the reaction will not proceed very far to the right. For our concentration of our ammonia, 0 plus 2x, whatever the 2x is, it's significant compared to 0. But because the reaction is not going to go very far, our value of x will probably be insignificant compared to the 0.5 that we're starting out with for the nitrogen and the 1.0 that we're starting out with for the hydrogen. So we are going to assume that our x value is much, much less than 0.50 and that 3x is much, much less than 1.0. The reason that we're doing this is so that we can ignore our x values inside our parentheses here. If we can ignore these x's, that will simplify our lives in terms of the calculations. The cutoff that we will be accepting is the 5% rule. Right? So as long as x over whatever we come up with for x over 0.50 times 100, as long as this is less than 5%, we're okay. And as long as 3x over 1.0 times 100% is less than 5%, then we consider our assumption to be valid. The reason for the 5% rule is that a lot of the measurement equipment that we will have access to in the lab isn't really accurate to all that more than 5%. So we wouldn't, in most situations, we wouldn't be able to measure more accurately than 5%. And so if we can't measure more accurately than 5%, there's no real point in calculating to a value that is more accurate than what we could actually measure. So if we assume that x is insignificant compared to 0.5 and 3x is insignificant compared to 1, then our equation becomes much simpler. We can leave those out and our k value becomes 2x, that whole quantity squared, over 0.5 times 1.0 raised to the third power. Now, this 2x, keep in mind that the 2 is within the parenthesis. So if we square everything, this would give us 2 squared times x squared, or 4x squared, over 0.5 times 1 raised to the third power. 1 raised to the third power is 1, so this would be 0.5 is equal to our k value. We are trying to solve for x, so we need to get x all by itself. So we will multiply both sides by 0.5 and divide both sides by 4. So we're going to take our value here, we will move it up to be with x, and then we'll take our 0.4 and we will move it down below our k value. Okay, so this gives us 0.5 times k over 4 is equal to x squared. We can get the x by itself by taking the square root of both sides. This gives us x. So x is equal to 0.5 times our k, that quantity divided by 4, and then we square root everything. So this would be equal to the square root of 0.5 times 5.6 times 10 to the minus 4. That whole thing divided by 4. So this will be equal to 0.008366 molar. In terms of significant figures, this is actually 5.0. We would cut it to 2 significant figures. Okay, to find our equilibrium values, we'll need a little bit of room, so I'm going to clear out some of our values, keeping our x. So we have x equaling 0.008366. We will need to cut and round between the 3 and the 6, and that's molar. We should check our assumptions. So that would be our first one, which is here. So we would take our 0.008366 divided by 0.50 times 100 would be equal to 1.6733%. So that checks out. That is less than 5%. So our assumption for the first part works. Now we will take 3 times 0.008366 divided by 1.0 times 100. That will equal 2.51%. So that one also checks out. Now the last thing that we need to do is figure out our concentrations as well as report on our extent of the reaction. First, we would have our extent of the reaction. So our extent of the reaction is our x value. That would be equal to 8.4 times 10 to the negative 3rd molar. Next, we need to know our concentration of N2. So our concentration of N2 would be equal to 0.50 minus x. Right? So we plug our x value in, and we get 0.4916. In terms of significant figures, we would cut that there. So our concentration of nitrogen would be 0.49 molar. Our concentration of H2 would be equal to 1.0 minus 3x. So if we plug in our x value for that, so 1 minus 3 times our 0.008366, we will get 0.9748. In terms of significant figures, the sig fig gets, because we're doing addition and subtraction, it gets cut at the 10th place, so it get cut here. And so we actually get back our original value of 1.0 molar. So in this case, it really makes sense to do our assumption rule. Our x was truly insignificant in terms of our sig figs compared to our initial concentrations. The difference gets lost in the significant figures. The last one would be our concentration of NH3. If we look at here at our equilibrium line, that is equal to 2x. So that is 2 times the 0.008366, which comes out to be 0.0168, with 2 significant figures as our number of significant figures. So this would be 1.7 times 10 to the minus 2 molar. Those would be our values for our answers. Okay. Let's now work through a problem that we will eventually find requires the use of the quadratic equation. However, we will approach this as though it was any other problem. So, we are looking at the decomposition of PCl5 to PCl3 plus Cl2 at 250 degrees Celsius. It has an equilibrium constant of 0.030. Now, the first indication that we might have some issue is that value of 0.30. Typically, if your equilibrium constant is close to 1, i.e. not greater than 10 to the fourth or less than 10 to the negative fourth, you may have issues where the assumption rule will not be valid. So, if a container has the following initial concentrations, the PCl5 initial concentration will be 0.100 molar, PCl3 initial will be 0 molar, and the chlorine, Cl2, will be 0.020 molar. What are the equilibrium constants for each component, and what is the extent of the reaction needed to reach equilibrium? So, first thing we would do is write out our chemical equation, giving us plenty of room. It is already written out, and so now what we can do is write down our ice table. So we'll start with initial, change, equilibrium, ICE. Our initial values are 0.100, 0, and 0.020. If we write out our equilibrium constant expression, that is K is equal to our products over our reactants raised to their respective powers. PCl3 raised to the first power times our chlorine, Cl2 raised to the first power, divided by concentration of PCl5. So if we plug our values in to see where we're at, to try to determine what the Q value would be, you can see that we would have a 0 located right here for the PCl3, which means the numerator is going to be 0. 0 over any number is 0, and so our Q is equal to 0. This tells us the reaction is going to shift to the right to form more products, increasing the concentration of PCl3. In fact, the reaction cannot shift to the left because we are missing one of our components for the backwards reaction. Without the PCl3, there is nothing to combine with the Cl2 to form more PCl5. So the reaction has to shift to the right. So the PCl5 will go down by some value x, PCl3 will go up by some value x, and the Cl2 will go up by some value x. So at equilibrium, we'll have 0.100 minus x. This will be x. And here we'll have 0.020 plus x. Plugging our values into our equilibrium constant expression gives us x for the PCl3 times 0.020 plus x over 0.100 minus x. Now, what we should do is look to see if the assumption rule is going to work. So we try it out and evaluate, is x less than 5% of the values that we're working with? So we're going to try to assume that x is much less than 0.020 and 0.1. However, if x is less than 0.020, then it is definitely less than the 0.1. So we only really need to check the first condition. So if we assume that x is insignificant, then we get an expression of k being equal to x times 0.020 divided by 0.100. This is equal to 0.030 because that is our value for k. If we move everything to the other side, we get our x is equal, multiplying the 0.030 by 0.1 gives us 0.0030. If we divide that by 0.0200, we end up with 0.15. Now, a quick comparison of this value to our assumption will quickly tell us that this is not a valid assumption. Our value for x is actually bigger than the 0.02, and so the assumption does not work out. So we will need to solve this without assuming that x is insignificant. So I will now erase our work for trying the assumption rule for x. Okay, distributing our x into our set of parentheses gives us our k value being equal to 0.020x plus x squared over 0.100 minus x, which is equal to our k value of 0.030. So in order to solve this, this is a second order polynomial, we're going to need to use the quadratic equation, which means we need to get all of our x's to one side and put it in the correct form. So we'll multiply both sides by our denominator. So that will give us 0.030 times 0.100 minus x being equal to 0.020x plus x squared. Now we're going to move all of our terms to one side. That gives us x squared plus 0.020x. If we distribute our 0.03 into the set of parentheses, right, we would get here plus, because we distribute it and then move it to the other side, so plus 0.030x minus our 0.030 times 0.1, which would be 0.0030. Okay, and this will equal 0. So combining our two x values gives us 0.050x for here. Okay, so that gives us x squared plus 0.050x minus 0.0030 equaling 0. For a quadratic equation, this part here, the 1 in front of that, the x squared is a, this part here is b, and this, including the negative, is c. Our quadratic equation is x is equal to negative b plus or minus the square root of b squared minus 4 times the quantity a times c, that whole thing all over 2 times a. So if we plug in our values, we get x is equal to minus b, so negative 0.050 plus or minus, so we will have two answers that we need to evaluate, plus or minus the square root of b squared, so 0.050 squared minus 4 times a is 1, 4 times 1, and then times c, which is negative 0.0030, square root that whole thing, divided by 2a, which is 2 times 1. We get two values for x, only one of which is going to make sense. The first value, if we look at the plus term, right, so if we add our value, we get 0.035. The other value we get, if we subtract we end up with x being equal to negative 0.085. Now we know that the second term, this one here that came from subtracting, cannot be correct, because if we plug it back into our ICE table, we would end up with a negative concentration here for our Cl3, right? And we can't have negative concentrations. So that tells us that our second answer here, our second possibility, is incorrect. So the one that we will be using is this for x. Okay, so we're going to do a little bit of cleanup and then wrap up with the answers. So we have our value for x that we worked out using the quadratic equation is here. We can now plug this into our values that we have at the bottom of our ICE table to figure out our concentrations at equilibrium. So our concentration for the PCl5, we find that by the expression that we have at the bottom of our ICE table for PCl5, which would be 0.100 minus x. Plugging x in, we get 0.065 molar. Our concentration of PCl3 would be equal to x, so that is 0.035 molar. Our concentration of Cl2 is equal to 0.020 plus x, so that would be equal to 0.055 molar. The last thing is the extent of reaction. That is essentially x. So our extent of reaction is how far the reaction proceeded, and in this case proceeded to get to equilibrium. So that would be equal to x, which is equal to 0.035. Okay, that is all of our answers for this particular problem.